pleased to be here with you today and to present our guests. I'm Andrei Pavlovich, artist in residence and pianist and composer. We will have the two external experts during this project. One of them is Sonia Lonchar, my duo partner from LP Duo. You will meet her in a couple of weeks. But today with us is Klaus Molmer from the University of Aarhus. We worked together on a project called Quantum Music from 2015, and thank you. We really did great things together, and Klaus is a really amazing person and scientist, and also very much into music and art. And this is where we see it's very important. His view on how the physics and the science can connect with the music and art in general. So I will let Klaus now to do the speech and the lecture, and then at the end we can talk more. You can ask questions, and yes, we are all here. So enjoy. Thank you very much, Klaus Molmer. Thank you much.
Thank you very much, Andy, and thank you very much for the invitation to come here. It has been a great pleasure for me to work with various artist colleagues, and I would like to share with you during this brief presentation how I have benefited myself personally very much from that, but also maybe some of the practicalities. How do we actually make it work to talk between expert audience or expert forum of scientists and the expert forum of artists and musicians, as we showed today. And I will give a PowerPoint presentation. So I just have to share my screen. So here we go. Just a second. This one. So we can see what we're talking about. So my name is Klaus Molmer. I'm a physics professor at the Aarhus University in Denmark, and I have given my talk the title Synesthesia with Quanta and Music. So let's start with the quanta. Let me first see if I can actually make my slides move. So I'm working in the research areas of quantum physics and a modern research area involving what we call quantum technologies. I've actually visited the Technical University of Delft several times before. This is one of the leading places in the world for experimental and theory efforts to build quantum computers, and that's a topic I'm working in also myself. Apart from my interest in physics, I'm also doing a lot of teaching. That's what we all do in universities, but also public outreach. So I'm speaking to school classes, and over the years, I've actually given more than 100 popular lectures to general audiences. I've written many articles, and I've also written a popular textbook on quantum mechanics in Danish. And then on the hobby side, I play the clarinet, the saxophone, and a little bit the piano, but just for fun, as I write here. I don't want to stand in front of musicians and call myself a musician. The synesthesia part of this talk, this is a painting by Kandinsky called Impression, or probably Impression. And what you see in the picture is, you probably recognize a grand piano and maybe an audience in the forefront of the picture. And I always see this big yellow spot on the right as being the music in the room. And I took the title synesthesia. Synesthesia was regarded a neurological disorder. Now I think it's maybe more regarded as a neurological talent, that some people are mixing up different impressions. So for example, associating colors with sounds, or associating colors to letters of the alphabet, as I show you up here. And this kind of connections in the brain are interesting and real in many people. And at a higher level, you could also imagine that the way we can paint music is also a kind of synesthesia. And in that sense, of course, I would like to see the collaboration between science and arts as a synesthesia. That is, can we take concepts or impressions from those two worlds and blend them together in a meaningful manner? So a meta outline of my talk is, I'm not going to talk about the art project, but I like to reflect upon how we're doing the art project. What is it like to discuss physics and music with composers and musicians? And what can we learn in that process? So as I told you, we're doing all these outreach activities. And so for me, I'm not an expert in communication, but I've learned myself doing the communication, because I've had various artists attending my popular lectures, coming up to me afterwards, asking lots of super interesting questions, but also sometimes proposing joint projects, and invited me to join their events which are just like a physics conference. That could be a conference for theater directors or a course given in a music conservatory. And that has been very interesting. And of course, that makes you reflect, how do I do that well? How do I deliver if I'm invited to give a talk in a conservatory? So this is very much about communication. It's actually the same reflections in my mind as when I do a popular outreach talk. I have to realize what is the expectations of the audience. And it's extremely fascinating for me to talk to what I call an expert audience of musicians. The kind of questions you get if you give a talk on quantum physics in a music conservatory, it's very, very different from the kind of questions you get if you give a popular talk in the city hall or in a movie theater in Denmark, where you will have a broad blend of people with all kinds of experiences in life. And the expert composers or the expert musicians, of course, react from their expert domain, and they will ask you questions that are flavored by that. And for me, it has been inspiring because it has actually been very good questions, very inspiring questions, also for my own research. And then I also talk about, just the tricks. How do you visualize the kind of physics I'm doing? I'm of course not teaching quantum mechanics to a layman audience by the equations. I'm trying to make analogies to the daily world. And if you talk to musicians, you don't use all daily world analogies. You use, of course, analogies from the world of music, because then you can penetrate much deeper, you can be much more precise. So that has been super useful and very exciting. And I'd like to share that with you. And then in the end, of course, how did we define some of the common projects? And I let a few of the projects speak for themselves, and then you can judge whether we succeeded or not. So Denmark is really a superpower in outreach, and I just want to brag a little bit about that first. So in the mid-19th century, that is 150 years ago, there were outreach schools developed all over the country. They were called Folkehøjskoler, and the intention was really that the rural population, the young people, should be able to go every week and learn something. It was the early days of Danish democracy, so you could learn about history, you could be educated to live in a democracy. And these højskoler, they still live today. And now many young people go there between high school and college to find themselves in life. They will have some art classes, but also learn practical skills and find out what they want to do with their lives. And I think this is part of the background why everything we do in terms of outreach has large audiences in my country. So we are essentially preaching from the podium. I'm standing up on the box. This is a case of beer, and then I'm telling everybody, here's a story about the quantum computer, and then many people come in to hear that talk. And I just again to brag a little bit, Aarhus, second largest city in Denmark, 300,000 people, 6 days every week. You can go and pick between 5 and 10 lectures on a scientific domain every day, right? So we have on the order of 50, 60 different popular talks every week that people can come and attend in the evening in the university. And they are fully booked, these talks. So there are really many people who have an interest in coming and listening to this. This is one of the talks. This is not myself, but a colleague who is speaking in the biggest lecture theater we have. This is not big enough. So in fact, we are live streaming these talks. So I gave a talk on quantum physics 2 years ago before COVID, and I had an audience of probably 25,000 people. Okay, so every little red dot is a place in Denmark, a movie theater, where the talk is being transmitted. And if you zoom in on this upper corner, then you can see how densely we are covering the country. And I show you the fishing boat because there's a small fishing village up here where 88 people live, and 64 people came for my talk on quantum computers. And that's not because you will see quantum computers inside fishing boats. Of course, it's because people like to come together. They probably have a coffee together after the talk. And the real joy is actually not the talk on quantum, it's the being together. But I think that's also what my artist friends will tell me. It's a social thing to go to a concert. It's a social thing to attend activities. So I think it's a win-win situation when we do these activities. And then let me come to the arts, because then I was gradually invited to attend events where there would be maybe a poet or a painter or a priest or a politician who would give a talk. And Imam was giving a talk once together with a Buddhist monk and a Tantra sex expert and me. So that was an interesting mix of people. And all of these events are perceived by the population as very entertaining. So people buy tickets for them and fill up the theaters when we do these kind of events. So that has been very exciting. And for me, it has become more and more attractive to join those events also more than the regular popular outreach, because I get a little bit more out of it myself also. So these are just a few of the things over the last few years, and what you see here at the bottom of the screen is actually Andrea and Sonja and one of the concerts in Copenhagen. And I want to highlight Kim Helveg, who will come up later in my talk, because he's really the one who approached me and asked if we could talk about quantum and music, and he brought me into this nice collaboration. Kim has also brought me into contact with the ballet. So he's working as a composer and piano player also in the Royal Theatre in Copenhagen, where they have a ballet school, and they created a ballet based on quantum stuff. And that was, of course, also great fun for me, but also very exciting experience. So let me come to the communication part. So many artists describe themselves as doing investigations. If you see many authors, many theater directors, you also see painters who say that we are investigating how the modern person reflects on this part of life, or how we act in these and these circumstances. And I think this is interesting, to think of the artist as a researcher and using the art form as research. At least it connects to me as a researcher, because I'm also researching things. So I realized that if this is the setting for what we are doing, then we can communicate as if we are investigating something together. So I like to communicate the physics, because that's my contribution to this investigation, to this collaboration. And here I like to say one thing, namely, I have to either insist or cheat my artist friends a little bit to feed a little bit more physics into their heads than they ask for. Because very often the artist would come up to me as a quantum physicist and said, I'm deeply fascinated by quantum jumps. And then they have already thought a lot about quantum jumps in some crazy direction, which is very far from what it means in physics, or entanglement, or the quantum computer, or the superposition principle, some particular esoteric phenomenon which truly enough exists in quantum physics, but which you can already start building your own crazy stories on. And I like to insist that you don't have to build artistic impressions on quantum physics to make it crazy, because it's already crazy. And so I'm willing to go in any crazy direction with the physics, but I like to first be sure that my artist friend knows that within the physics, within the standard textbook, within what we do in the laboratories, all the crazy effects are already there. I mean, we don't have to invent telepathy or some supernatural connection between minds to understand the effect of entanglement. You can go out on this campus where they actually made the first really demonstrated entanglement over kilometer distance between particles far apart, being connected in a way described by my equations or our equations in physics, and studied by equipment in the laboratory. So it doesn't have to be as mental as it can be made sometimes by the artist, but what we are exploring is, of course, how we can make it something that speaks to the mental or speaks to people who are not physicists. So there's a little bit of a popular lecture I like to give the artist, where I try to tell as much of the real physics, and then we can build on the real physics instead of starting extrapolating without that common background. And then, of course, I really like to communicate also to the artist how our phenomena are described, how we are relying on our results, which methods we are using, the way we think, and the way we communicate and illustrate our science, because that is really what we're going to investigate together. And therefore it's very good that, I mean, I think I have an impression of how the working artists work, and you can see documentaries with composers and painters, but you don't see the same kind of documentaries with a scientist saying, how do you get inspired? How do you do these or that things? So I think that's interesting to it's maybe the thing we explore in this project more than the actual science. So now let me show here inside this talk, a talk inside the talk. So I just in a few slides present to maybe the physics or scientists in this audience today, how I communicate science to the artist, right? So you may know everything I tell you, but then you can reflect upon, is this or maybe a good or a bad way to communicate some physics facts to a particular audience. And this is not what goes directly into the art, but it's after having done this kind of presentation with my artist friends, then we have a common basis. And then we can follow that basis or we can deviate from it. But we know that this basis exists in our common vocabulary. So I like to talk a little bit about classical physics. That's the physics before quantum physics, because what makes quantum so interesting is that it is different from classical physics. But that's a very natural thing for a physicist to say. But if you don't know classical physics to begin with, then of course it's not different from anything. So I like to show that we have this physics and then we change that physics. And the classical mechanics can also be illustrated with music. So I like to think of the classical mechanics as the physics of music, meaning that I describe some music phenomena with a classical physics. And then I move on to quantum mechanics, which I call the music of physics, because funnily enough, some of the things that are hiding music and music instruments is at the very core of quantum mechanics. And I like to emphasize that, in particular, talking to musicians. And then finally, of course, we get to how quantum can be used as inspiration for music or arts in general, and this synesthesia idea that we can bring really inspiration across. So let me try to give you now a few simple physics slides explained via music. So this is Pythagoras, and I think everybody who went to school learned this formula that you see written on the slide here for the sides, the length of the sides of a triangle. Pythagoras is also famous, in physics books at least, for having studied the sound of vibrating strings. So he had this string board, and you play the different strings, and he was actually the one observing that if you have a string and you play it, then if you block it at the half length, then you place the octave tone, right? And of course, this is used when you play string instruments. You put your fingers on the guitar string and you shorten effectively the length of the string and you play different tones. So Pythagoras was noticing that, and Pythagoras was really extremely fascinated by numbers. He had a religious belief in integer numbers, and the fact that you can cut the string in 2, in 3, 3/5, all these integer ratios of the string, that they give rise to these particular harmonies, was for him a deep proof that mathematics rules the world. And people even went so crazy, including Pythagoras himself, to believe that everything in the world is ruled by real numbers. For example, there's a phenomenon called the music of the spheres, where some people thought that the planet orbits have a kind of integer ratio to each other in how long time it takes for the Earth and the other planets to encircle the sun. And that would be fully in line with Pythagoras, but it's kind of nonsense from a physics point of view. Of course, a planet can sit in any distance, and there's a physical law which tells how long time it takes to get around the sun. Let's just jump 400 years, 500 years later to Ptolemaios, who lived in Alexandria, current Egypt. He was the famous astronomer, I think the best astronomer up until the year 1700 or so. But he was also interested in music. And in fact, he made a music theory. He was looking very much into the harmony and what is called the circular fifth, where there's actually a small mathematical discrepancy, which is accounted for in different ways. One is called the Ptolemaic comma, which is a correction to the music scale that was developed by him. This both shows that, of course, ancient natural philosophers were interested in phenomena like music, but it also shows that there's a regularity in the way we make sounds that could be discovered by these guys. And that regularity is, of course, something having to do with how the music instruments work. So what I show you here is a violin, and then I show you a violin string, and you can see how the violin string is moving up and down. And the reason that a violin string always makes the same sound when you pitch it is because it has no choice. It has to vibrate at that particular frequency. Or it can also, like you know from rope skipping in the schoolyard, if you vibrate at twice the frequency, you can make this figure 8. And that's actually an overtone that also exists if you pitch the string on that violin. And you can also pitch higher overtones, and then you get higher and higher frequencies. So mathematically, I can denote by F the frequency of the sound. And then when you play the string, it will also play twice the frequency, 3 times the frequency, 4 times the frequency, depending on how many of these wobbling motions up and down exist at the same time. Now, this is a clarinet, Swedish clarinetist, Martin Fröst. And it's a little bit of a different instrument because it's open in one end and it's closed in the other one. So therefore, you don't have the same condition. You actually have a maximum motion of the wind in one end and a minimum motion in the other end. So here it fits half the length of the pattern you see above. It could also fit 3 halves or 5 halves. And therefore, the harmonies of the clarinet will be a tone that can be anything, but the next overtone is actually not twice, but 3 times it. So this is why, if you're a clarinet player, you don't play the octave as the first overtone, but the fifth within the next octave. And that's something physicists can say with excitement. And actually, this is in the textbook. I took the pictures from the first year textbook in physics that I'm using when I teach physics at university. But the pictures of the instruments, I had to put in myself in the talk. So take a piano. On the piano, you actually have the basic tone governed by which key you play on the piano. So what I show with the blue bars is just the frequency, a graph of the frequency. You can see they're increasing as you move to the right on your instrument. And in fact, you're increasing for every half tone by nearly 6%. Okay? And that means that if you go through 12 half tones, then you have increased by a factor of 2. And that's the octave. So that's why we have the 12 half tone steps within one single octave. So that's the building of the instrument. And the reason the octave sounds so good when you play it together with the ground tone is because you're already playing it, because the string already plays it. There's actually not an absolute sense that twice the frequency sounds particularly good in your ear. For musicians, obviously, but for non-musicians, we cannot hear that. But we can definitely hear if that frequency played by that key is the same as the frequency which was also played by that key to begin with, or if there's a dissonance between those two. So this is why these harmonies are so nice. And I show you also the fifth here, which is also a very particular interval. And that's a particular interval because of this formula. Because if I take the string, then if I take the double, it's here. If I take 3 times the frequency, that vibration of the string, I end up very close to this G in the next scale here. If you know what the piano looks like and what it plays. In fact, the number of the frequency of that key on a real piano is not 3 times that one down here. It's 2.996 times the frequency down there. So it's close enough that we think this is really good. And it's always almost what I would call magically close, that you can get this nice harmony of the piano. And then I just plotted in the other frequencies from that formula. And you can see I start putting the arrows a little bit displaced compared to the middle of the keys, just to indicate these are actually not keys on your keyboard, but they are sounds which are being played when you press that key down here. And this is, of course, where real music appears, because there are sounds now that appear that are interesting. Now, that was classical mechanics. Now, of course, I can get carried away by that, but of course, every musician is probably even finding some of what I said now a little bit ridiculous, because they already know that and they know much more than I do about this. But I just wanted to present a physicist's view on it. And now I want to just tell you that the physicist does not only observe these string motions. We actually know they are there because they obey a physical law set down by Isaac Newton. So Newton made the relationship between force and motion. Force is equal to mass times acceleration. And when you apply that formula to every element of the vibrating string, you will find that the solution is that the string is vibrating. And you will find exactly the frequencies I showed you. So this is a simple mathematical exercise. And while Pythagoras, he said that it's the numbers that rule the world, the physicists will say, no, it's Newton's laws that rule the world, but they actually reproduce those numbers because they are the solutions you get. So there's a reason for Pythagoras numbers ruling the world, and that reason is called Newton's law or classical mechanics. Now, there's more than the string to an instrument. So whether you play the violin or guitar, the way the sound makes it to you is actually because it's getting amplified by the body of the instrument. And what you see here is when the guitar is playing a deep or high-pitched tone, then the whole body will vibrate. So this is like a big loudspeaker playing a deep tone, or this is what the guitar surface actually looks like when it's playing a high tone. This is recorded with a radar, the same way as the police measures your speed in the road. And then you can see these images of how the guitar is actually moving when it plays these. So the loudspeaker, the instrument, is actually more the body of the instrument who's transmitting the frequency to your ears through the air. And of course, other instruments have similar patterns. The drum skin itself moves in these patterns. The sound pressure inside organ pipes are moving in these pressures. So that was classical mechanics. Now, quantum mechanics. Quantum mechanics started by solving a kind of mystery. If you look at light, you know, you can break light through a prism. You can look into the sky when it's on a rainy day and you can see rainbows in the sky. That's actually all the light coming from the sun, which is being split into its different frequency or color components. And these different color components, as far back as 200 years ago, could be very precisely split into different directions. And then you could measure how intense is the light at the different colors. Okay. And what is done here is that you have taken the light from the sun, and then you've just shown the red and the yellow and the green and the blue colors. But what you also notice is that there are dark stripes here and there. And these stripes were a mystery, except every stripe, and there are 100,000 stripes in the spectrum of the sun, can actually be identified with some matter that exists on the ground. So if you drive on the highways in the evening, you have these orange street lamps. And inside these orange street lamps, there's a gas called sodium. And sodium burns in this orange color. And that's exactly the orange color of the dark stripe here. So we actually know that there's sodium in the atmosphere of the sun. And we know what all the other stripes mean. In 1850 or so, there were some stripes found that they could not find an equivalent on Earth. And they named this funny stripe after a new material. And that new material was a kind of sun material, so they named it after the sun. Sun is Helios in Greek, and therefore it was called helium. Okay. Now, of course, all of you know helium. Helium was observed for the first time in the sun, but in the 1860s, it was discovered on the Earth also. But it's a gas which is very light, so it actually does not exist in the atmosphere. But it comes out from natural gas, it comes out from radioactivity, and we have all the helium we need for balloons and whatnot. But it was actually discovered in the sun spectrum before it was discovered on Earth. Every stellar object you can see through your telescopes can be analyzed in terms of its colors, and therefore astronomers know exactly which atoms are on every object they can see in the sky. And that's a talk by itself, because it's mind-blowing that it works like that. And it's really, really impressive. It's really the basic of the microscopic understanding of how stars were ever formed. And now, of course, you know they're looking for extra Earth planets in the galaxies. Will there be life out there? And one step to go there would be to look for the same gases as are necessary for life on Earth. Can we spot those gases in the planets around other stars? Okay, let me not get carried away, it's just fantastic. But we are a little bit in the same situation as Pythagoras. We have seen some frequencies, but we don't know why. I remind you that it was only Newton and his laws that could really tell us why the strings were vibrating like that. And now we have this funny thing, but we have no clue where do these colors or frequencies come from. So again, we need a new theory, and we need a physicist to come with that theory. And this was, I can proudly announce, a Danish scientist, Niels Bohr, who in 1913 made his so-called model of the atom. So he said all this matter we're talking about is actually composed of atomic nucleus, and around the atomic nucleus there's a single electron, or there are more electrons that are flying around. Okay, and this is not a radical model, but it was brand new in 1913, because at that time we had just discovered, not we, but our colleague, French physicists, had just discovered the atomic nucleus as a particle. And we're having electrons who are negatively charged and a nucleus who is positively charged. We know there's an attraction between them, and it's like the gravity attraction. So therefore, the same way as Earth is bound in orbit around the sun, the electron could be bound in an orbit around the nucleus. And that is what is shown in the stamp here on the right. That does not explain why there are only very specific frequencies of light coming out of the atom. For that Bohr, he made crazy postulates. He actually said, we do have the electron who orbits as a satellite. But then after that, he said, you cannot orbit just anywhere like the satellites or planets can do. You can only orbit at those particular distances. Okay, why those distances, he did not precisely tell, but he could make a formula for these distances. And when you are in this orbit, you don't radiate anything, but you may jump from one orbit to a lower one. And it is such, that's why we build rockets, that it takes energy to go high up in space, but if you go back in space, you release the same energy. And that released energy, in this case, is released as light. So if you go from a high orbit to a low orbit, then the energy difference between those two orbits is released at light with a certain energy, which is the same as frequency or the color of the light. So these very specific frequencies that exist in the hydrogen atom, for example, could be explained if the electron can only be on these particular orbits in the hydrogen atom. And that's the Bohr model of the atom, which I think is taught in physics school in most of the world today. And it's a super good model, but it's really postulates. It's not a formula that gave these results. It's actually a model without formulas. And Bohr could make some formulas, and he could make super good arguments why it would be true, but it was still at the level of postulate. And physicists don't like that. In fact, we don't call that physics. We call that a model. So a French scientist, Louis de Broglie, he said, maybe what makes these particular orbits so interesting allowed is that there is a phenomenon that prefers those particular distances. And now you can see we're approaching a little bit the same thing as this music thing. I mean, why does the violin play these particular tones? And we found there was a reason. And de Broglie, I don't know if he was a violin player or a flute player or a musician, but if he had been a musician, it would be a great story. Because he said maybe what is characteristic for these orbits is that there's something like a string that just matches a certain number of oscillations around that string. So I'm indicating that here with this red curve, that the green circumference just matches a number of oscillations up and down, but it bites its own tail, the same way as the violin string is fixed in both ends. And this is a wavy phenomenon. That's the same as the waves on a string. So therefore, Louis de Broglie has actually introduced a wave-type description of particles, except that, of course, it's only a picture. But he sort of suggests what should this wavelength be, because it has to be a fraction of the full period around here. And from Bohr, we knew what was that full period. So therefore, we actually have formulas for this wavelength. The real theory had to be a wave theory like the theory of strings. So here we have, of course, the violin strings, but here we also have Newton's equations, and we have a so-called wave equation, which is actually the one we solve when we want to understand the vibrating string. So could we also get a wave equation for this electron, and not just a picture of waves on a PowerPoint? And here it is. Okay, so I just jumped to it. And now if you're a physicist, then of course you know this equation, and you can read this equation as well as I can. If you are an artist, you should look at this equation the same way as I look at a painting in an art museum. I mean, it's beautiful, right? And it talks to me in some way, but it's not perfectly defined how it talks to me. But just for the non-physicists to know, this equation does not look any more complicated than the equation who describes the surface of a guitar, who is moving under vibration sound, or actually the vibrating string, or many of these other different music instruments have equations that look just like that. And the equation components are similar to the ones. In fact, Schrödinger did not have to invent the concept of such an equation. He just had to try different variants of such an equation, and then it turned out that this one worked very well. So here I show you water waves, and that's a complex phenomenon. It's described by an equally complicated equation, which was perfectly known at the time of Schrödinger. But here we don't really know what we're describing. When you solve it, you get these beautiful patterns. So these are all different solutions, which are no longer Bohr's orbits, but are solutions to the wave equation. But if you look at the frequencies at which these patterns are oscillating, then you find that the difference between them correspond exactly to the frequencies of the light emitted by the atom. So you're reproducing the same result as Bohr's formulas do, but here you have actually solved an equation that gives these results out. So that's really nice. I also like just to point out to you that I have showed you the picture of the guitar before, and you notice that this pattern is also in the atom, right? Two areas that are bouncing up and down, and this pattern with the 6 is also in the atom. So here there are also 6 patterns bouncing up and down. So in fact, the atom is just a tiny guitar, if you like. And of course, you could have other patterns corresponding to the other ones you see here in the Schrödinger picture. What does the wave function mean? So one thing is the frequencies going up and down. And the fact is that the frequencies we can calculate today are with 12-digit precision. Oh, sorry, I have to go back because if I can. We can calculate these energies very precisely. But the question is, what does the actual shape mean? What is it that goes up and down in the atom? And here's a picture of Olivia Newton-John and John Travolta. And they have absolutely nothing to do with the story, except that Olivia Newton-John's grandfather was a German scientist called Max Born. And Born, he made the interpretation of that wave function. He said that the values of that function that Schrödinger has calculated are telling us how often we see the particle if I do measurements. Because if you can actually go in and ask, where is the particle? We can never tell precisely where we will see it. It will pop up some random place within that blob that I'm showing on the screen here. But the probability that it will be in one particular point or some other point are given by the values of the function. Okay, so that's a strict prediction. And if you do 1 million experiments, then you can validate that you are equally often on the left and on the right of that picture. And you are more often in the middle with a certain fraction than outside this image. So quantum mechanics is a completely predictive theory, except it cannot predict the outcome of a single experiment, which is fundamentally random. That's one of the crazinesses in quantum mechanics. So when we're talking physics with musicians now, I'll tell them about this quantum mechanics. We'll talk about how the atoms are actually little music instruments, how the quantum mechanical world gives you frequencies which are very characteristic. We can maybe use that as a creative thing. The music instruments could mimic how these wave functions are doing things, or we could maybe think about sound as something that's composed of different frequencies, the same way in the music world as in the quantum world, where we are doing all the efforts in the laboratories to actually put these waves together and steer their motion. And then there's this what I call randomness and collapse, which is also interesting. So the wave particle, this electron, is nowhere and everywhere at the same time. It's something we call superposition states, which is well known for any wave phenomenon. If you play two keys on a piano, you get the two wavy patterns, and your ear can actually hear that as superposition and interference. That also exists in the quantum world. Interesting creative material. The wave particle can never be completely at rest. The more compact you try to make the wave function, the faster is the motion of the particle inside that. And that's a fundamental law in quantum mechanics. So you can really not put anything at rest. So imagine a guitar string which is completely at rest. Well, in quantum mechanics, it can't. It will always be vibrating a little bit. And our composer friend, Kim Helvig, actually once composed music recording the silence in a concert hall and just increasing the volume. And suddenly, of course, you could hear all this small creaks and cracks that is in any room. And that was a kind of music out of nothing. This exists in the quantum world all the time. It's never completely dark. You cannot turn off quantum light. There's always some fluctuations of electric and magnetic fields, even if it's completely dark in the room. Empty space is not really empty. It's actually an inferno of particles and their antiparticles that come and go all the time. Again, this principle that nothing is completely at rest, because you can virtually, as we call it, borrow energy and do crazy stuff as soon as you hand it back again fast enough that nobody discovers. And quantum mechanics sets a law for that you cannot discover it if you're fast enough. So all these things are happening all the time. So there's a myriad of activities in the quantum world. And then there are these modern things that we study also here at Delft, where we actually engineering states which over long distances have some correlations with each other. Spooky action at a distance is the term quoted by Einstein for these crazy things. Teleportation paradoxes that we can talk about and see if we can visualize that, or if we can use that as a creative engine for our artist friends. So how does this sound to you? How do we go through all these things? I'll just show you a few examples. So let's call it an investigation. So I'm sitting down with Kim, for example, and then I explain some of these things that has caught his mind. And then I explain by analogy. If I'm to explain superposition, I tell him that, well, it's nothing more than playing two keys at the same time at your piano. That's not very creative, and that doesn't create very exciting music. If you want it to be something that people could feel and hear, and it could be something nice to listen to, you could also just play two different tunes at the same time. And then you would have something which was, again, two things at the same time in a quantum sense, but it would maybe be more interesting, something you could relate to. You could make the tunes depart and meet again in unison. You could make one major, one minor. You could make many things to illustrate some of these other things. And every time I say that, of course, I don't think that this is the great idea for music composition. I'm not the composer, but I'm pretty sure that the musician understands what I'm talking about. And then Kim goes away and he never does what I suggest, right? Of course, because he's the composer, I'm not, but I'm sure he understood what I was talking about. And I can explain Feynman diagrams. I can explain particle physics and say, look, this is what the physics is. If you want to explain particles and antiparticles appear from nothing and disappear again, why don't you have complete quiet? And then suddenly you just have two tunes that start and then meet again, okay? Because that's the particle and the antiparticle. One major, one minor, one being high tones, one being deep tones. Actually, an antiparticle propagating from A to B is the same as a particle propagating from B to A backwards in time. So you could also do a little bit like Bach and have a tune, and then you could play the same tune backwards. And that would be the antiparticle. And they could be played at the same time, which I'm sure Bach already did over and over again. And in fact, that is a visualization of this. And again, I'm not instructing the composer or the musician to do that. I'm just explaining that this is maybe also a good way for you. And some of the pictures I've made of the diagrams from the physics textbook, Kim prints them out on sheet music paper. Okay, and then suddenly Feynman diagrams become something that goes up and down, and then he walks around looking at it. And then wherever inspiration comes in his head, I cannot tell. But then after some weeks, he cranks out some really nice music, which is inspired by this. So I will, maybe you could say that every time we pick a certain topic, it's not so much that this is the way you make music out of that topic. It's more, this is creating some limitations. Now you can only work in this space where you are working with these type of things. And then it's those limitations that open a new universe for the music. So let me now give you some very concrete examples. So we have been discussing with Kim and Sonia and Andrea, who are here, Dragan, who's in Belgrade, sound engineer. So we try really not to illustrate physics phenomena by the music, but rather to interpret or exploit these music phenomena. So here is the way with Kim that he has made some new music based on some new tones you can make, actually based on atomic frequencies. So in the end, the limitation for this music was that we were only allowed to play the same frequencies as are emitted by a hydrogen atom, scaled down to the audible range. We have recorded image and sound from labs in my department, sent them down to Dragan, and he has turned that into tonal material that could be played on electronic instruments. We have the Feynman path and diagrams, which is this particle physics phenomenon. And then with the choreographer, we have also used Feynman diagrams as a kind of choreographic material. And again, with the choreographer, I was explaining, how do I explain superposition? I can have two dancers doing almost the same entanglement and whatnot. And she nodded politely. And she had actually super good questions to what is the concept of entanglement? What's the concept of the collapse of the wave function? But of course, she didn't go home and make a ballet that was as if it had been made by a physicist. That would have been really boring. So let me just quickly take you through these easy technical parts. So the formula on top of the screen is the Balmer formula, it's the Rydberg formula, telling what are the allowed frequencies coming out of a hydrogen atom jumping from the state number n to state number m in the sequence of Bohr orbits. And then you get all these differences in energies as the allowed frequencies. And if you take the second series, the Balmer series, then you're going to get some numbers, which are the ones written here. And I've written them like that because these numbers could be played as audible frequencies. And then you can hear them, okay? And then Kim instructs his computer to play these tones for him for a couple of weeks. And then just before he goes crazy, then he turns it into music and composes music based on these tones. And then, of course, we can do the same with some of the other scales. This is a boring scale. The atomic physicist will know that the Rydberg series converges. So you actually have a good step between the lower two ones, but then they get clustered towards the same tone in the end. So this has kind of limited potential, maybe even better then. But if you go somewhat higher, for example, to the sixth series in the atom, so you end up in the sixth shell from the seventh or eighth or onwards, then you get more equidistant frequencies and you get more different tones to play, so to speak. So there's a different tonality to these different series, and you can compose a piece of music composed of little exercise pieces, or where each of them has a component of the spectrum. And that's exactly what Kim was doing, writing down what are the tones, playing with me. I just want to show you, this is the kind of diagrams physicists used in the 19th century to depict where these frequency differences come from. And in fact, the same kind of illustration we used when we talked to Kim about the music. So here's the performance of this music, and it was actually close to here, played in The Hague in 2017, but it was also played in many other places. Please send me an email if you want the link to this. There's a YouTube video where you can actually see the whole concert and hear it. It's really great. I should also say that at the performance, I've had the pleasure of participating. So the performances at some places been talk plus concert. And then I stand on stage, like here, and then without PowerPoint, of course. And then I talk for 10, 15 minutes about the process and what people are going to hear and what it's all about. And then we have the music, and that has been a super exciting experience. Kim also made a concert for Sinfonietta and solo cello, inspired by the physics of so-called Bose-Einstein condensation. So that's something many atoms do when they're cooled down. And I gave a talk on instruments. So this is from one of the events in Aarhus actually, where we had this Sinfonietta behind me, and they gave me the permission to use a screen. I said I love to use the harp and the cymbals and all these different instruments instead to introduce some of the physics concepts. That was great fun, and so I had fun. The audience had fun. There was a string concert, there was a wood and flute concert, there was a brass concert inside this concert, meaning that you could get the impression that these groups of instruments actually came together the same way as atoms do in Bose Einstein concerts. One thing that's a little bit funny about this, you can see the musicians also very happy, is that often this nice orchestra outnumbers the audience at the concerts, okay? Because this is contemporary advanced music, and it has a loyal audience of 15 to 20 people, which is regrettably the same week after week, okay? And they look happy here because we have an audience of 300, because this mix of the lecture, which is already well branded, and then this thing is just huge. We played the same thing in the opera in Copenhagen, and the guard told me afterwards, they never saw that many people for these open concerts as now. So I think the combination, it's not because I'm a very good speaker, it's just because, wow, that sounds kind of funky. Quantum physics and music, and we will hear a little bit about the physics, and then we will hear the music also. So it's that part of it is also an interesting part. And the audience look happy. So she always looks happy, that's my daughter. But, anyway. And then the ballet, I see that time is running a little bit out, but let me just say that I was approached by a choreographer. Actually, with Kim, we gave a talk in the Friday Bar, another celebrated Danish institution. We like to bring beer in Denmark, in particular every Friday. And the students in the ballet school in Copenhagen invited us to come and talk about this before they opened the bar. So we talked about the quantum stuff, and one of the choreographers was really interested. And she said, I'd like to come and talk with you. So she read my book, and then she came, she had notes everywhere. And then we were discussing some of the material. So this is Kavli AiR, who then choreographed a ballet. And it was really based on Feynman diagrams, which was both a guide to the music that Kim wrote for the ballet and also for her choreography. And it was, again, a great event. So actually, they performed the ballet with the dancers. It was an outdoor event. Oh, sorry. In a big tent, but people were crowding outside. I think we had like 500-600 people watching it. And then I did the typical physicist thing, because I said, then I think after the performance, of course, I was talking, I was illustrating how I had talked to Kavli AiR, making my own amateurish movement. And then, of course, she did just like Kim, she went home and did something really interesting, contrast to what I had suggested. And then we had the performance where I spoke about that. And after that, I said, let's have a question session, because you can only show people something if you also give them a chance to ask questions. And we had more than a full hour of questions after this thing to all of us. So it was actually super interesting, and also for the musicians and for the dancers and the choreographer to be exposed to all these questions from the audience. So maybe a proposal to theaters is to, after every performance in the theater, you should allow people to ask questions to the actors, and something fun could come out of that. So anyway, let me come to my final reflection. So I showed you this picture in the beginning, and saying that, well, I mean, here's how a painter can interpret music. And of course, artists are the experts in reflecting on our life and experiences and putting it into a form where it's also up to the viewer to see how that matches your own experience in life. And I think that's very interesting to try to use that in a creative process with the sciences. There's actually, again, this synesthesia idea, of course, that at a really high level, maybe we can integrate the Schrödinger equation with the arts. This is the Schrödinger equation inside the picture. I think it's probably by Turner. And I'm very sorry, I should have found a familiar picture and put him instead, but I didn't have the time this morning to change that. So it's we humans who make the science, and of course we are using our own brains to invent what we do, and therefore any inspiration going into our brain is important in this process. So let me just conclude why I think that this is true, or why I think that most scientists would find this plausible, could be illustrated by a crazy question or crazy phenomenon that every year when they award the Nobel Prize, they have a roundtable discussion. And at least in the old days of TV monopolies, there was only one TV station in my country, and they would show everything cultural. So you could sit there, the whole country, and watch these Nobel Prize winners, old white men, talk about how they got their fantastic ideas. But they always had the same question asked at the end: do you believe in scientific intuition? And it was interesting to hear this reflection in their minds. How did they get their ideas? And of course, you also can reflect on how you get your own ideas. So here is not an old man, actually, but a lady who got the Nobel Prize in medicine. You've been thinking about something without willing to for a long time. Then all of a sudden, the problem is open to you in a flash, and you suddenly see the answer. What is it that happens in the brain of a scientist when this is happening? To me, it happens when I'm brushing my teeth. It's never happening in my office. It's always happening when I do something else. And it's often happening where I have a feeling that it was actually something physical in my surrounding that made it click in my brain. If you try to permute your knowledge, nothing comes out of it. You must give a sort of mysterious pressure and then rest, and suddenly, bing, the solution comes. There's another aspect that I would add to it. I really like this one. And that is, I think, taste. Taste in almost the artistic sense. Certain individuals see art in some undefinable way, can put together something which has a certain style or a certain class to it, a certain rightness to it. And I think as a theoretical physicist, I probably share with many colleagues that we are not only looking for the right equation, it also has to be a nice equation. I mean, it has to be a good-looking equation. It has to be a simple equation. So there's an element of aesthetic. Everything that is right in a simple science as physics is also nice, nice to look at. And driven by that, of course, it limits us, but it also releases maybe the optimism and the creative space in which we can make progress. So I think this is where there's a similarity to the arts, but also a genuine hope on my side that I can actually cultivate my own way to steer my intuition. I have an intuition which is extremely much guided by vision and extremely much by physical motion, but very little by sound, for example. And by thinking more and more in sound, maybe my next physics idea could be out of a tune in my head instead of a picture in my head. So let me just finish here. And I think that Niels Bohr would have loved quantum music. So I just show you a quote from Bohr, I think one of his best quotes. And he said once, we must realize, because quantum is so strange, we all talk about quantum physics in a strange way sometimes. And Bohr is the founding father, and he had this statement about quantum physics. We must realize that when atoms are concerned, language can only be used in the same way as within poetry. Also, the poet is less bothered about describing facts than about creating images and establishing mental connections. Okay? So the way that we are talking as scientists about the microscopic world is not describing facts, but actually describing how we understand the phenomena we see. And I think that Bohr could have said exactly the same about music or ballet or painting, but now he picked the poets who give this quote. And with this, thank you for your attention.
Thank you very much, Klaus. Thank you so much for your presentation and lecture. And I would like to invite people, if someone has any question, please be free to ask.
There is someone with a question, Nikos.
No, this is a clapping hand. I don't want to push anybody. Sandra has a question, I think. You can unmute yourself.
Hi, yes, Klaus, first of all, thank you for a wonderful talk. And I'm actually quite envious about what you explained about the Danish outreach program. And I wish we had something like that here in the Netherlands. I think it's very important to make this connection, between science and society, first of all. But then about your talk. So you focus a lot on the harmonies in music, right? And the pitch, basically, how that relates to quantum mechanics, which makes complete sense, of course, and it's a beautiful analogy. But there's another aspect of music which you didn't touch, which is rhythm.
Yes.
And I've heard, I might be wrong, but that there are certain non-human animals that actually can understand rhythm. And I've not heard of any animals that can understand harmony in the way we do. So I think that when it comes to musical intuition, rhythm is even more basic, even a lower level than harmony. So do you think there are similar links also to science in the rhythm aspect of music?
I think that's a fantastically good question, of course. And you could say that the periodicity that we get and time-dependent regular temporal phenomena is already in the harmonies, because a certain pitch is also a rhythm. It's just that we don't perceive it as rhythm, but as that particular sound. But I agree with you that the creative material in rhythm is huge, and I like this because it's simple physics. If I should go into something with rhythm, maybe I'd like to go to some of these interesting critical phenomena that actually give you beats at certain frequencies. Not the Q-switch laser, but maybe something highly non-linear, Van der Pol oscillators or whatnot. And I think it contains all the same possibilities to sit down with, for example, a musician and say, look, here is rhythmic material. And then Kim Helveg would say, wow, that's super nice. Let me build on this. And of course, we can also, I mean, if we just want to give something and it's going to be interpreted by the artist, then of course, we can quite liberally take time-dependent signals that we measured anywhere and say, look, this is what exists out there, and then see what you can do with it. But thank you very much for the remark. You're absolutely right. There's much beyond just the harmonies. And this was mostly for the illustration purposes that I picked.
Yeah, thanks. Wonderful talk.
And if you want to build your outreach program, in 2005, we started these big lectures and we advertised them heavily, and we had 500 coming for 10 talks about Einstein. And then we said, we do it again. And the next year we had 1,000 coming. And then after 5 years, we had 2,500 coming. So I think the persistency is the only thing you need. Every physicist I talk to say, we also have an open house day at our university, and 500 people come to the big institutes in Germany, for example. And then I tell them, did you ever try to just do the same every Saturday? Because if you do it every Saturday, you would actually have cohorts coming every Saturday. So it's nothing special about the Danish population, but it takes some energy and some coordination to keep doing it year in and year out, of course. But I think we are perceived now as being in Aarhus equivalent to going to the movies. And actually, the people who come for my talk, I can hear through their conversations. Some of them don't even know who's speaking and what is the topic. They just step in because it's always fun to go to these talks, right? Like going downtown to a cafe. But you have to know it's there, right? Because that's why you come in the first place.
Great. We should talk about this more. Yeah.
Yeah.
Thank you. I would like just to ask you, first of all, thank you for speaking about intuition, because for us as an artist, it's something very important.
Sure.
You know, when you said you were brushing your teeth and something, you know, just came to your mind, it's also when we compose, like we start to work, you know, some team, and then nothing is happening, and then another day the piece is there, and that's so beautiful. And in music, I'm impressed with all the time, and Sonia and me are talking a lot, and we are very impressed with the dualism of all the things, you know, and also when you talk in science, and also when you talk about the mind, okay, intellectual intuition, but in the science too, wave particle in quantum physics and many other things. But also in the music, you know, we have like classical music concerts, but we also have the new contemporary music concerts. And what you said, that's amazing concept of the silence, actually. That the room that is recorded, because without the silence there is no music, because you know, but it's also the truth that when we go to the most silent room in the world, we will hear two sounds, you know, our nervous system and our blood pressure. So something is going out without us taking the part of it all the time.
Yeah.
So do you think actually we can connect, we can speak about the silence in a way about the quantum vacuum?
Yes, it's fun because I was invited to there was an event in Brazil, a conference last fall on quantum music type thing. And actually the main theme of that conference was the vacuum and the silence. And I look so much forward to come to that. I think that some of the ideas we are working in physics, the quantum vacuum, these things are super interesting because they, at least for us, they offer a picture of having things in vacuum and having things emerge from vacuum. In particle physics theory, also largely developed here in the Netherlands, actually by famous scientists, there are many quantities, we call them vacuum expectation values. And they are actually, all the physics is expressed as something we calculate in a nothingness, but then we we create the particle first, let them do something and remove them again. Then we ask, what is that process? Which number represents that process? So I think that conversation is good. And of course, again, in the end, particle physics is not my mental state, and it's not the state of music. It's maybe the vocabulary and the different experiences we have that are interesting to exchange. But I think it's super exciting. I also think that what you said about having our heartbeat, we actually, just like the question we had from Sandra Otte before, we have a sense of rhythm. We have a beat, and we also have a heartbeat that can go up and down, and we can have a sense of time, which can change because it's psychological. Also, when we listen to music. And so that is actually also interesting to explore, compare with the physicist view on what is time and what is our feeling of time and relative time. So absolutely.
Thank you. Is there more questions?
It's also possible to ask in the chat, but then let's just see if there is a chat. No, there are no questions in the chat. Yeah.
So I really like the part where you inspire the artist and not like go from physics and throw it through a Python code and then generate music.
Yes.
But I know that's also happening.
Yes.
So can you compare those two somehow? Do they influence each other?
Yes, thank you for the question. Yes, you can go on YouTube and on the internet and you can Google quantum music, and then you will find this, but you will also find many other places where they are really enacting a physics phenomenon. So they are more literally listening to what the physicist asked for, and then they say, here's the entanglement piece or something like that. And I'm sure that the composers and the musicians doing that, they're still using all their professional skills. So they're not just doing a work that was ordered by the physicist. And so therefore, I think the impression can be just as good or as nice as what you get out of this work. I just think this is more fun, because I think this is a more open process. And I think that, but I don't know the people, so maybe they're talking together the same way, but at least on the outset, this has a higher respect from both fields towards each other. I mean, I'm not regarding music as a way to illustrate physics at all in this project here. I regard music as being fantastic, and I'm deeply honored that musicians think they can get some creative material out of physics. And now I just want to present it in the best possible way so they can pick what they like. And the other projects are different, but at the end, the product can be the same because they're professionals. I've heard only a little bit of it. I mean, when we finally restrict him to certain tones, then maybe it's not so different from if I'd given him a Python script that would give the same. In fact, I did do that so he would have the material to listen to. So at the end, the process is maybe not so different. I prefer our style, and I would never come and ask you to do something, but I like to present it in that language. But please do something else.
There is a question.
No, I just open the chat here, see what happens. So sorry, this is a very vertical question. Vertical. Okay, that's not for me. Is it possible to see the recorded talk? Yeah. So if somebody's nodding in the room, so I think it will be available after the talk.
Yes, it will be available. We will send a link to everyone. Okay, if there is no more question, I really want to thank you, Klaus, for a wonderful lecture and inspiration, and we can, finish this talk, and we will have more time of it. We can finish with maybe, like dualism as a change, or as a tool for change or improvement, and that's what we actually doing with the communication between arts and science.
That would be the fulfillment of our dreams. Yes. Thank you very much. Thank you for your attention.
Thank you. Thank you. Thank you.
Applauding there.
There's applauding. Okay, then we leave.
Yeah.
Then we leave the screen on.
That's a silent upload.
Yeah, that's fine. That's how it is.
That's even used also for the performance as a quantum thing.
Yes. These are the Zoom days.
I think that there was this raised hand. But
there is also the upload as a.
Okay. Yeah. Okay.
Thank you very much.
Thank you very much. Yes.
Now I leave the meeting here, but you still have what